Welcome to lecture number 43 of the course on nonlinear structural analysis, theory and applications. Okay. So, let us recall what we have done in the previous lecture. So, in the previous lecture, we started discussing distributed plasticity approach, okay, and we started with the stiffness based formulation, which is also called displacement based formulation, okay, and we saw that the element formulation assumes that the strain is constant along the length of the element and the curvature is assumed to vary linearly along the length of the element, which these two are a kind of severe limitation when you are modeling a structural systems or a beam with this displacement based element. Then what you have to do, you have to use many elements in regions where inelasticity can develop. Okay. Today we will look at an alternative formulation which is called the flexibility or force based formulation. Okay. So, let us get started. So, if you recall what we have done in the stiffness based formulation, okay, for nonlinear analysis, we maintained compatibility. That means, this V is the element end deformation or element end displacements in the simply supported basic or deformation coordinates, and then this A matrix is a matrix of shape functions, okay, and that gives us this V bar x. V bar is for the section level, deformations at the section level, and x stands for any distance x measured from some reference position. Okay. So, this is our compatibility relationship, and then we use the action-deformation relationship, which is incremental section force is equal to the section tangent stiffness matrix multiplied by the incremental section deformation vector. Okay. And then what we did, we enforced the equilibrium using the principle of virtual work, virtual displacement, right, and we derived these two relationships. What is the first one? First one is relating the section forces S bar x with the element end forces S, and the second one is the element tangent stiffness matrix in the basic or deformation coordinates in terms of the section tangent stiffness matrix K bar x, which is integrated between 0 to L. So, as you can see, the compatibility, action deformation and equilibrium, the three principles of mechanics, are actually used to develop the element formulation. Okay. In linear analysis, if you recall, we did exactly the same thing for stiffness based or displacement based structural analysis. We start with compatibility, then we impose force deformation, and then finally we impose equilibrium and then solve for the unknown displacements delta 1, delta 2, theta 1, theta 2. If you go back to lecture number 2, you will see this, and this is the idea for displacement based method like slope deflection and moment distribution. Okay. So, basically there is a similarity, I mean it is identical, right. On the other hand, what we will do today for the flexibility or force based formulation, we will maintain equilibrium first and then we will use the action deformation relationship, and finally we will enforce the compatibility using principle of virtual work, virtual force. What we did for linear analysis, if you remember, in the force method or flexibility method, we start with equilibrium, then we use force deformation, and finally we enforce compatibility and solve for unknown redundant forces, which I am denoting x1, x2 and so on. This was again discussed in lecture number 2. So, you can see that basically they are identical. Okay. The approach is identical. Only difference is that in nonlinear analysis, the element formulation is flexibility based, whereas the overall analysis is still displacement based, or we can say a direct stiffness method. Then the question is, how do we implement this flexibility based formulation in a standard finite element program, which is based on the direct stiffness method. Okay. So, we shall see that. So, let us go ahead and use this and develop the element formulation. Okay. So, the flexibility based formulation. So, as you remember in the previous lecture, for a 2D beam column element in basic or deformation coordinates, which we introduced in lecture number 42, and we have done the same thing in direct stiffness method. Okay. So, mi, theta I, moment and rotation respectively at end I, mj theta j moment and rotation respectively at element end j, and capital N is the axial force, delta is the axial deformation. If we cut at a distance x, then the moment mx and axial force nx are exposed. Okay. So, the element end forces is denoted by the vector S n mi mj, and element deformation vector is denoted by V, which is delta theta I and theta j, and the section forces are denoted by S bar x, which is axial force nx and bending moment mx, and corresponding section deformations are epsilon x, the strain at a reference axis, and psi x, which is the curvature. Okay. So, this formulation of flexibility based method, which I will go through, was first proposed by Kaba and Mahin in 1984. Okay. So, let us first invoke equilibrium. As we said, we will first use equilibrium. Okay. So, let us say this is the element. I am considering first mi, bending moment at I. So, if this is the bending moment, this is 0, there is no load present in the element in between the two nodes. Okay. Then this is my bending moment diagram. If this is the bending moment diagram, at any distance x, the bending moment is simply x by L minus 1 into mi. You substitute x is equal to 0, then you get m is equal to minus mi, because this is the bending moment that is producing hogging. Okay. And if you substitute x is equal to L, then you get m is equal to 0. So, which is this, and in between the variation is linear. So, we exactly know what is the value of mx. Now, if you impose mj, then this is the bending moment diagram, and again you can calculate what is the bending moment at any distance x. If you apply axial force n, then you know at any distance x, the axial force is constant, which is equal to n. So, that means we exactly know how to calculate the section forces at any distance x if my element end forces are known, right. So, I can now write this in a matrix vector form. So, my section forces nx and mx can be written as this matrix multiplied by ni, mi, mj. So, this is my vector of element end forces, this is a vector of section forces, and this is the force interpolation matrix, which I am calling B of x. Okay. So, x is to remind us that this is at a distance x. Okay. So, S bar x is equal to B of x multiplied by S, and this equation is exact no matter whether your element is undergoing inelastic deformation or not. Okay. The bending moment distribution, the axial force distribution is exact, okay, even if you have element load in between. For example, if you have distributed load, you can draw the bending moment diagram and you can exactly determine what is the variation of the bending moment. So, therefore, equilibrium is strictly satisfied even when element loads are present. Okay. So, now let us talk about the section constitutive relationship. So, let us revisit what we did in the DB formulation, that is displacement based formulation or stiffness based formulation in the previous lecture. So, we said the incremental section force vector ds bar x is equal to the section tangent stiffness matrix multiplied by the incremental section deformation vector. Okay. So, this is what we did in the previous class for displacement based formulation, and we also said that we can use a fiber section modeling, which was covered earlier, or a stress resultant plasticity theory, which was again covered earlier, to determine this k bar x. Okay. And for a linear elastic section, we also showed that k bar, the section stiffness matrix, which is independent of x for a prismatic member, and this is for elastic condition, this is EA 0 0 EI. This is what we did for the displacement based or stiffness based formulation, right. Now, for flexibility or force based formulation, what we are going to do? We are going to write it just in the opposite manner. So, we will write the section incremental deformation vector is equal to the section tangent flexibility matrix multiplied by section incremental force vector. Okay. So, F bar x is called the section tangent flexibility matrix. Just like for the displacement based element, we could use fiber section modeling and stress resultant plasticity theory, we can do the same thing for flexibility or force based formulation. And again, for a linear elastic system, the flexibility matrix is going to be 1 by EA 0, 0 and 1 by EI, just inverse of this matrix. Okay. So, that means I can write this is nothing but KE inverse. Okay. So, now we have used equilibrium and we have used section constitutive law or action deformation. Okay. Now, let us talk about compatibility. Okay. So, let us say that for a given section force vector S bar x, section deformation vector V bar x is known. Okay. What we want to get the element deformation vector V which is compatible with the section deformation vector V bar x. So, compatibility relates the section deformation with element deformation. Okay. And we also want to get the element tangent flexibility matrix in basic or deformation coordinates which we are calling FV, such that the element incremental deformation vector is equal to the element tangent flexibility matrix multiplied by the element incremental force vector. Okay. So, how do we do that? To do this, we have to use the principle of virtual work, but now this time it is going to be virtual work, virtual force. Earlier, for the displacement based or stiffness based method, we use principle of virtual work, virtual displacement. Now, we will be using principle of virtual work, virtual forces. Okay. What is the principle? It says the strains and displacements in a deformable system are compatible and consistent with the constraints if and only if the total external complementary virtual work is equal to the total internal complementary virtual work for every system of virtual forces and stresses that satisfies the equations of equilibrium. Okay. So, the total external complementary virtual work is equal to total internal complementary virtual work. Now, what is complementary work? Well, if you take a bar and you pull it, okay, apply some load incrementally, right, and if you plot the force versus displacement, let us say it is nonlinear and it is like this. So, gradually you are increasing the force from 0 to some value, right, this value. Then we know that the work done, the strain energy is basically this area, right. This is the strain energy that is stored in the bar, the work that is done by the applied force. Okay. On the other hand, this one, this area, okay, this is called the complementary energy. Okay. This is called the complementary energy, right. So, when I say the complementary virtual work, that means let us show you are here applying an incremental virtual force. So, then this area is basically what we are talking about. Okay. So, now let us apply it. So, consider a compatible state of deformation, that means V bar x, my section deformations are compatible with element deformation V. Okay. Now, apply virtual forces delta S. Okay. Delta is used to denote virtual quantity which causes corresponding virtual section forces delta S bar x. Okay. Then the external complementary virtual work is delta S transpose V. Okay. That means this virtual force is riding through this displacement. Okay. Delta S bar transpose V. Okay. Internal complementary virtual work, that is delta S bar transpose V bar, and then we have to integrate it from 0 to L for the entire length of the element. Okay. Then what I am doing, I know that S bar x, that means my section forces is equal to Bx multiplied by S, right. So, that means if I make it virtual quantity, then this becomes like that. Now, if I do a transpose of this, then this becomes transpose, that means delta S transpose B transpose x. Okay. So, this is what this is replaced by that quantity. Now, since delta S is independent of the integration, it is taken out. Okay. So, now what I will be doing, this is my external complementary virtual work and this is my internal complementary virtual work. I will equate the two. So, if I equate the two, this is what I get, right. Now, this is true for any virtual force delta S. Okay. That means V is equal to this quantity, right. So, that means the element in deformation V is equal to integration 0 to L B transpose x B bar x dx, right. This is the formulation we are trying to develop, which relates the section deformations with the element deformation vector. Okay. Now, we have to still get the tangent flexibility matrix for the element. Okay. To do that, now consider that incremental element deformations dV causes a compatible incremental section deformation dV bar. Remember, bar is used at the section level. Okay. So, now let us apply virtual forces delta S, which causes corresponding virtual section forces delta S bar x. Okay. So, what is my external complementary virtual work? Well, delta W star external. So, the star is used to indicate it is complementary, is delta S transpose V plus dV. Okay. And what is the internal complementary virtual work? Well, internal, this is my internal virtual force at the section level delta S bar transpose x, and this is the deformation at the section level V bar x plus dV bar x dx. Okay. Now, what I am doing, this quantity I am writing again delta S bar transpose as I did earlier. So, what is my S bar? This is Bx times S and then whole transpose, and this is delta. Okay. So, then this becomes delta S transpose B transpose x. This is what I have written here. Okay. V bar x remains as it is, this dx remains as it is. Okay. Then this multiplied by that, I am doing the same thing and writing delta S transpose 0 to L B transpose x and dV bar x dx. Okay. Note that this quantity, what is this quantity? 0 to L B transpose x V bar x, we just now derived that this quantity is nothing but my element deformation vector V. Okay. Now, looking at this, what can we do? So, let us write dV bar x, which is the incremental section deformation vector, is equal to section tangent flexibility matrix multiplied by section incremental force vector, right. Now, this ds bar x I can write using the force interpolation function Bx, this is multiplied by S. Okay. So, for this I am substituting that here. So, this gives us 0 to L B transpose F bar x Bx multiplied by, this is D multiplied by ds, and then dx remains as it is. Okay. So, this is my internal complementary virtual work. Now, let us equate the two. So, if I equate, this is external complementary virtual work and this is internal complementary virtual work, and this equation must be true for any arbitrary virtual force delta S, right. So, therefore, what I get, that if you multiply this and if you multiply this, this two will cancel. Okay. And so, we get dV is equal to this quantity, where ds is independent of the integration. So, 0 to L this quantity multiplied by ds. Now, this entire quantity I am calling Fv, the tangent flexibility matrix, because what we have, incremental deformation vector for the element, which is equal to a matrix times the element incremental force vector, right. So, this is my element tangent flexibility matrix, okay, in the simply supported basic or deformation coordinates. So, Fv is 0 to L B transpose F bar B dx. Okay. So, if you consider a linear elastic element which is prismatic, okay, then using the section flexibility matrix from equation 8, what was the section flexibility matrix? Fe was equal to 1 by AE 0 0 1 by EI. Okay. If you use that and if you use the force interpolation function which I showed you earlier in equation number 3 and then multiply and do the integration, this is what you get. And this is the same thing we derived in lecture number 3 in direct stiffness method using alternative means. Okay. Now, let us talk about the element tangent stiffness matrix. So, what we got here is the element tangent flexibility matrix. Now, in a finite element program which is based on direct stiffness method, we need the element tangent stiffness matrix. So, how do I get the element tangent stiffness matrix? Well, I can invert the element tangent flexibility matrix. So, if I invert it, I get directly kV. Now, once kV is determined, which is in basic or deformation coordinates, okay, what I can do, I can transform this and go to the global coordinate, that is Q. So, I am calling it KQ. If you go to lecture number 4 in direct stiffness method, we did it, we derived this. Okay. So, we can get KQ. Now, consider all the elements that are present in a structure and assemble all the KQ to get the global structure level tangent stiffness matrix K for the entire structural system. Okay. So, now in a standard stiffness based finite element program, okay, element deformations are calculated first. If you recall, when we do the nonlinear analysis, you go to lecture number 14 or the direct stiffness method, you will see that we calculate the nodal displacement, incremental nodal displacements, right. From there, we extract the element end displacements in global coordinate. From there, we determine the element end deformations in the basic or deformation coordinate system. Okay. That means, element deformations are calculated first corresponding to an applied external force increment, right. Then we perform the state determination just like we did in the displacement based or stiffness based formulation. So, then how can we implement the flexibility based approach where my element end deformations are not input? Okay. So, therefore, the implementation of state determination of a force based element for a given element deformation is not a straightforward job, because my element end deformations are known in a standard stiffness based finite element program, whereas the flexibility based element formulation does not take element end deformation as an input, okay, as we have just now seen. So, therefore, we have to do it iteratively, and iterative state determination procedure was developed by Specon et al. In 1996, which is typically used. And whenever you are doing iteration, that means something is satisfied considering some tolerance. You cannot satisfy exactly. And what are those? The nonlinear section constitutive law and compatibility are satisfied within a specified tolerance. Okay. So, although I said that in this course we will not be focusing on the implementation, okay, but I think it is a good idea to get at least some understanding of the implementation of this force based element. Okay. So, therefore, let me go through how the state determination is done at the structure level and then at the element level for a flexibility or force based element. Okay. So, first, like I was saying, we calculate the incremental external applied load vector. Let us say RE is what you want to apply in n number of steps. So, you divide that, this is your incremental externally applied load vector. Let us say the structure level displacement is 0 and initially RE is equal to 0. So, internal resisting force vector is equal to 0, the structure is at rest. Then you assemble the initial element stiffness matrices, get the capital K for the entire structural system. Okay. Now, for each incremental load, okay, you calculate RE is equal to RE, that is initially 0 plus delta RE. Then your iterations start at the global level. Okay. So, for iteration I, we calculate the unbalanced load, okay, which is RU is equal to RE minus RI, right. We are just going through the Newton-Raphson procedure, which we have introduced you in the introductory lecture. Now, check if RU satisfies convergence criteria. Okay. Now, I will go through convergence criteria for this approach. If yes, then you go to the step 2 and go for the next increment, right. This is done in a loop. So, naturally for the first iteration it will not be satisfied. Okay. Then what we do? We calculate the incremental displacement vector at the structure level, which is delta r. K delta r is equal to RU. You solve for that and determine delta r. Then we get the current structural displacements, which is previous plus the increment. So, this is the current displacement vector at the structure level. So, for each element from this displacement vector, we need to now perform the state determination to get the element and forces capital Q in global coordinates. How? We shall discuss. Okay. And then also need to form the tangent stiffness matrix in the global coordinate for each element, right. Once these two steps are done, then we can assemble to get capital K and assemble this to get the internal resisting force vector, and I can set I is equal to I plus 1 and go to the next iteration. Okay. Let me focus on this element level. How do we deal with this for a flexibility or force based element formulation? Okay. So, determine the element deformation. So, you determine delta V from delta R. So, basically I am just writing it to one step. Basically from delta R you get delta Q and then you do AVQ multiplied by delta Q to get delta V. Okay. Then update this element deformation, you have initially V plus delta V. So, this is your current element deformation. Then your element level iteration starts. Just like I said, you have to do it iteratively, you cannot do it directly like a stiffness based or displacement based formulation. Okay. So, element nodal force increment, which is delta S for the jth iteration, is equal to the element tangent stiffness matrix multiplied by the element incremental deformation vector. So, when you start this J is equal to your 1, then this KV0 is KV from the previous global iteration, that is I minus 1th. Okay. And delta V1 is delta V, which is this quantity. Okay. And then you update the element nodal forces. So, Sj is the previous one plus this computed incremental element forces, right. And S0 when j is equal to 1, then S0 is the S from the previous global level iteration. Okay. Then for each section, once you know an estimate, this remember this is an estimate of the element nodal forces. Okay. If it was correct, then the state determination is done here. How did we get this? We got this using the tangent stiffness matrix of the element, which cannot give me, this product cannot give me the incremental force, right. So, this is a linear step that we are doing considering the tangent stiffness matrix, right. So, therefore, after we got that, for each section using the force interpolation function, we can get the incremental section in force, which is B into delta Sj, and we can also get the section force vector, which is B into Sj. Okay. Now, once I get the section force vector, this one and this one, okay, I can determine section deformation increment, which is some residual from the previous step. What is that? I will tell you in just a little bit. When we start the first iteration, then this is equal to 0. Okay. Then I will say what is the residual, plus I am using the section tangent flexibility matrix multiplied by the section incremental force vector, which I just now computed. Okay. So, this is an estimate of the section deformation increment, right. Then what I do, I update the section deformations. So, this is my current section deformation vector, which is the previous plus the computed incremental. Okay. And again, when j is equal to unity, then this is equal to V bar x from the I minus 1th iteration at the global level. Okay. Now, once I know this, once I know the section deformation vector, then I can do a state determination to get the section tangent flexibility matrix and the section resisting force vector, just like we did earlier using fiber section discretization. So, now this I am calling S bar R. The subscript R indicates this is the actual section resisting force corresponding to this section deformation vector. Okay. Now, as you can see, this corresponds to the computed section deformation vector, which is this, okay, whereas this section force vector is in equilibrium with the element end forces. Naturally, this one and this resisting force, section resisting force vector are not identical. So, there is a difference, and what is that difference? That difference is called the section unbalanced force vector. We put a subscript u. So, S bar u is Sj, this that satisfies the equilibrium, and this one that satisfies the constitutive relationship at the section level, of course, with the computed section deformation. Okay. Now, once I get the section unbalanced force vector, using the section tangent flexibility matrix, I am determining an estimate of the section unbalanced or section residual deformation. This is what I was mentioning earlier. This is the section residual deformation, right. Now, if you recall, we have derived the element tangent flexibility matrix equation. So, at this stage, when I do this, I have determined the section tangent flexibility matrix, which I shall integrate to get the element tangent flexibility matrix. I invert it to get the element tangent stiffness matrix. At this stage, I will check for convergence at the element level. If yes, that means if the convergence is satisfied, go to step 1 for the next element. If not, then continue with the next step. What is the next step? Now, I calculate the element residual unbalanced deformation, which is violating the compatibility. How do I do that? I derive this relationship, if you remember, without u, okay, that this is my section deformation and this is my element deformation. Now, if I have the unbalanced section deformation, then if I use this integration, I get the element unbalanced deformation. So, this is what is violating the compatibility. So, the idea is in the next iteration, when I said j is equal to j plus 1, I impose negative of that on the element, okay, and go to step 3 and repeat this procedure. Step 3 means I come back here, okay. So, this is the negative of the residual in the previous step, okay, and I follow the same procedure until convergence is achieved at the element level for every element, okay. There are other procedures also. For example, Neuenhofer and Filippo developed a non-iterative state determination procedure which relies on the Newton-Raphson type iteration at the structure level. What I just now went through, you have two iterations, one is at the global level and the other one is at the element level. Okay? So, in this procedure that they have proposed, that you do not need to do iteration at the element level, you can rely on the structure level iteration and still get a solution. So, I have also done some work on this. So, we have developed an implementation with fixed number of iterations for using this with explicit direct integration algorithm. So, towards the end of this course, I will discuss about the direct integration algorithms for nonlinear dynamic analysis. Okay. Here also you are not doing any iteration at the element level, and since we are using explicit algorithm, there is also no iteration at the structure level, and this works quite well. Okay. So, now let me talk about briefly the element convergence criteria. So, element level iteration is stopped when typically the normalized energy increment, which we say NEI with a superscript j for the jth iteration, is less than a tolerance, let us say ETOL. Okay. How do we compute this? This is computed as energy increment at the jth iteration divided by the energy increment at the first iteration j is equal to 1. When this is less than this specified tolerance. Typically, I will show you the tolerance value in just a little bit, and then this one I compute as the incremental element force vector for the jth iteration transpose the incremental deformation vector for the jth iteration at the element level. Now, this too I can rewrite like this, where this is the negative of the unbalanced element end deformation from the previous iteration, and this is equal to that quantity, okay, which we have seen earlier, right. Okay. Then Eij is for the first step where j is equal to 1, and again this can be calculated like that. Okay. Delta v is from the ith iteration and kv is from the I minus 1th iteration at the structural level. Typically, E tolerance can be taken as 10 raised to the power minus 16. So, you can see this report for more information on other criteria that can be used. Now, the energy criteria controls both the unbalanced forces and the residual deformations, hence it is better. Okay. When an element reaches its peak strength, the stiffness matrix can become ill conditioned and unbalanced forces can be small, while the element residual deformations can be large. So, therefore, if you use a criterion based on element deformation alone, then your iteration may not stop, okay, because of the large element residual deformations. Okay. So, energy is the only measure which accounts for both unbalanced forces and residual deformations. Okay. So, therefore, it is better. Okay. So, with that, let me summarize what we have done in this lecture. So, we have talked about flexibility or force based formulation and how it is implemented in a standard finite element program or a structural analysis program which is based on direct stiffness method. Okay. So, the implementation part may appear a little bit difficult to follow, but if you are interested, if you are doing your own implementation, then you can go back and listen the lecture a few times, you will be able to understand. Otherwise, you can skip that, but at least you got the idea of this force based or flexibility based formulation. Okay. In this case, equilibrium is strictly satisfied and no assumption is made related to the distribution of axial strain along the length of the element or distribution of curvature along the length of the element, unlike the displacement based or stiffness based formulation. Okay. Therefore, this is a better approach of modeling structural system, and I will show you in the next few lectures that one beam in a let us say multi-story building, a beam, complete beam can be modeled using one flexibility based element, whereas if you want to use displacement based element, then you have to go for more than one elements, especially at the ends where plastic hinges are going to form. Okay. So, in the next lecture we will talk about the numerical integration. With that, these are the references that I have used in this lecture. Okay. So, with that, thank you and see you in the next lecture.